So I'm introducing Josh in lieu of his supervisor, Catherine Nish, who's I guess on maternity leave right now. So Josh did his bachelor's and I believe master's degree at Georgia Tech, looking at glaciers and ice fracturing on Europa, which I'm going to guess was with Brittany Schmidt. And then is moved on to a PhD at Western, where he is now, working on impact cratering on Titan with Catherine. And so without further ado, Josh, tell us about your research.
First thing I should say is that I did my master's at Western as well. So my bachelor's were at Georgia Tech. But okay, let's talk about biomolecules on Titan. Okay, so first let's start with a brief review of just Titan itself. So Titan is Saturn's largest moon. It's one of the largest icy moons in the solar system. But what makes it unique isn't its size, but rather the unique atmosphere, the very thick atmosphere that it has on top of it. And the atmosphere is composed mostly of nitrogen and a little bit of methane. What happens is over time, cosmic and solar radiation will ionize and dissociate these particles, meaning the molecules are basically broken apart into their individual atoms. And over time, these ions will recombine to form longer chained organics out of these individual atoms or ions. And hold on. And among these, are these tholins, these things that are considered precursors to biology, basically a prebiotic material known as tholins. And before I elaborate on those, I should say that they're not just in the atmosphere, they're all over the surface. So what we're looking at here is an image of sand dunes made of these same organics that are in the atmosphere on the surface of Titan, compared to those that are sand dunes that are on Earth. And these aren't small, they cover a large portion of Titan's surface. They are all over the equator and they wrap all the way around it. So basically Titan's surface is covered with this prebiotic material that, if it could be oxygenated, could begin to produce things like life or things resembling prebiotic life. So I wanted to just talk about what happens to tholins in water. So what happens is that you get these organics and they basically get oxygenated. They take one of the oxygen from the water and they can begin to form amino acids. And essentially what we're comparing here is just how quickly they can begin to form, and how, given enough time, more can begin to form. And this is important when we think about time, because as far as the chemistry and the origin of life, it takes time for chemistry to evolve and to form. And the more time we have, the more evolved we might expect the chemistry to make it. So the question then becomes, how are you going to get liquid water on the surface of a moon that is 94 Kelvin on the surface? And there are a few ways. The ones I want to focus on is an impact crater. You have a comet, it'll smash into the surface. This giant shock wave will cause material to be excavated out. And also, it'll also send a heat wave through, or shock wave that will heat up the bedrock material, and it will basically melt a small piece of it. And while on Earth the bedrock may be molten rock, here it's molten water. And while the image here may show you a thin layer of melt, it's actually pretty thick. It can be hundreds of meters thick if the crater is large enough. And while it will begin to freeze immediately, it can take hundreds to even tens of thousands of years before it's entirely frozen. And the reason this is interesting is because when we think about the chemistry that's there, mixed with this liquid water, and the amount of time that it could have to evolve is really
can I pause you a second? Just
longer than we could ever consider modeling or experimenting in the laboratory on a human time scale. And that, of course, is the motivation behind the new Dragonfly mission from NASA. Basically, this has just got funded a few weeks ago. This is really exciting. We're going to be sending a quadcopter to the surface of Titan and going to be searching for biomolecules on the surface. And one of those places they're going to be looking is going to be the impact crater on Titan, which begs the question, okay, where should we expect it to be? Because these puddles aren't going to be liquid anymore. They're going to be frozen, which means we need to understand what happens to the chemistry as it begins to refreeze. In particular, how can we access the material in the ice? So if we imagine a melt pond of some depth h, and it freezes over time, the assumption is that because it's freezing from the top and bottom inward, it's going to concentrate all of the inorganics in the middle as fresh ice begins to form. We say this based off of, say, terrestrial sea ice, so we know most of the salt gets rejected as sea ice forms. Now, what we do know is that in reality, a little bit of salt gets frozen into the ice. That sort of at the question then is we then ask the question, okay, if some of it gets frozen in, how much, and is it enough to do any type of experimenting on? Could we sample a piece of the upper layer of ice to look for trace amounts of solute instead of having to get basically hundreds of meters below the surface to access this material? So I want to test the assumption of how much of the impurities will be concentrating into the interior by adapting this planetary ice model that was developed by Buffalo et al., where they basically tracked how ice or how a seawater ice would reject salt on Earth and in Europa sea ice. Except I want to adapt it to a Titan environment where we look at HCN or any other type of organic solute in place of salt. Now, the reason we use an HCN is just because we know it's on Titan and we know it has the potential to form amino acids, and it's also simple, meaning as far as its initial stages, it's important for us to be able to adapt the chemistry from salt to organic we understand. And then from there, we can assess the likelihood of retrieving a sample at a given depth. How far down do we need to be able to go? And then we can also think about how will this vary for different chemistry. And then from there, we can also think about the timescales and sort of use that to infer the amount of evolution that could happen with this type of chemistry when we think about going from prebiotic to potentially an origin of life. So I want to start by just explaining how the model works by looking at a terrestrial example. Say we had a pond of salt water and it froze. It's going to freeze from the top down, rejecting most of the material to the bottom. The trick is that because we know a little bit of it will get frozen into the ice, what really controls that is going to be the thermal gradient. Basically, how quick is it going to freeze? At the surface, it's going to be the coldest. But you have a cold surface with a warm water, so it's going to freeze very quickly. And because of that, you can have a slightly higher amount of salt freezing than lower down where you get a thicker ice layer, so slower freezing. But in the end, it's going to freeze at the bottom. And the way they track this was essentially, assume this is, say, 100 meters deep. What they would do is they would look at the top portion, take 1 meter cross-section of this water, and then they would model how each centimeter, the chemistry and physical properties of a centimeter within each centimeter within this meter will evolve. And then once that upper centimeter freezes, it basically stops, saves the data for that 1 centimeter cross-section, and then starts the model over, shifting it down by 1 centimeter within that sort of 100-meter depth. And it basically just repeats this over and over, going through the entire depth of the profile. You get this entire 1D look at how much salt would be freezing into the ice here. Now, if we compare this to a Titan scenario, it'd be very different for a couple of reasons. First off, we're dealing with organics, for example, HCN, instead of salt. And the big difference here is that it is going to be less dense than water. So we won't have the same buoyancy effects. And then two, we're freezing in two directions, not just from the top down. So really, we can start to think about it from two different directions. We have freezing in the top layer and freezing in the bottom layer. Now, the top layer is going to freeze very differently because the HCN is less dense than water. What that means is you don't have the same buoyancy driving it out of the ice. So as the ice freezes, the water is just going to stay put. Sorry, the HCN is going to stay put. And the amount of HCN you'd expect to freeze into the ice would be equal to whatever the bulk salinity is of the liquid at that time. And we base this assumption based off terrestrial examples. We look at, say, different types of rock in a molten lens, where if the rock is less dense, it basically stays suspended and will freeze into that matrix. While on the bottom, we could think about it being much more analogous to a terrestrial environment, where because it's more buoyant, what that means is as the bottom layer freezes, it's going to reject out most of the HCN. With just a little bit freezing more at the top, but as the thermal gradient decreases, you have less, until of course it meets in the middle. The trick here is that as it rejects from the bottom, you're going to have an increase in the bulk salinity in the liquid layer, meaning the upper layer will then get progressively more concentrated as it begins to freeze. So the way we've been approaching this problem to model it is essentially looking at the bottom layer rather than the top, where we have to model how at some depth it will start to freeze, and how much we can quantify how much will freeze out at each centimeter, and then from there we can know how much would be rejected into the melt. In the same way, we look at it from a meter perspective. modeling for each centimeter, and then sort of shifting it up throughout the profile to get a complete profile of how much is getting rejected. The result being that we can basically get a bulk salinity within the ice at any given depth. And because it takes so long to do this, because we're looking at a centimeter, we're basically processing each centimeter in a meter, going through hundreds of meters of ice. What we're doing is we're looking at basically a 5-meter section throughout the depth and going through there. And from there, we can sort of extrapolate. Now, we're still a work in progress. We have a few more points we want to gather. But the end goal would be, this idea will be, for a given bulk salinity, say of 5%, we can then have a profile of what the concentration would be at any depth, which then correlates to a thermal gradient, or basically whatever the temperature gradient is at that point, you would expect this much salt to be freezing into the ice, or sorry, HCN. Then moving forward, what we'd have to do is basically consider not 5%, but 10%, all the way up to say 50%. Because if we assume the bottom layer is going to be rejecting and increasing that middle layer, we then would have to consider the same scenario, but higher concentrations. So once that is done, once we have this basically three-dimensional matrix of basically bulk salinity with thermal gradient or depth over some initial concentration, we can basically begin to model it from a 2D heat transfer model. This is how it works. So imagine we have this pond, and we have a thermal gradient at each point along the wall, from the bottom and the top of this melt lens. Because we know what the thermal gradient is, we can basically go back to this plot that we have and look at what the thermal gradient was for a given concentration, and then look at how much the bulk salinity was at that point, and basically say, okay, it's freezing. We know it would have had this amount, so we basically say, okay, it's freezing with that amount of bulk salinity. And we continue that step by step, basically freezing inward slower, or more, inch by inch, basically, where we have a new thermal gradient, and then it freezes, and we can then infer what the salinity would be at that point. And then from there, we can get a precise estimate of this two-dimensional look at what this model would be like, not just a 1D perspective. So to review, basically, the Dragonfly is a new mission going to Titan to investigate potential biomolecules in the ice, in one place being impact craters. So what I've been doing is adapting this planetary ice model to try and quantify the distribution of these organics they're interested in basically sampling, to help them target, help them understand where to target, and also help them understand what it is they're targeting. Because while what we're looking at now is HCN, if we were to consider, say, a future problem where we think about different organics, say amino acids and nucleobases, these are as dense as or more dense than water, which would basically mean we'd expect it to have the inverted relationship, where the majority of these organics are going to be further down. And while not all advanced organics are going to be denser than water, these are examples of some that would be more difficult to access, as opposed to, say, a simpler, less evolved HCN molecule. And so thank you, that's my work. Oh, sorry, I had my volume down. Are there any questions?
Well, thank you so much. Yeah, we can do a round of questions, maybe a few questions.
Are there any plans to do experiments on this?
So no, well, let me put it this way.
So are you guys doing experiments?
So Buffo et al., I'm working with Dr. Brittany Schmidt here in Atlanta, and basically her grad student, Jacob Buffo, and her other grad students have been, or are working on basically testing this model where they would look at samples from terrestrial ice. So they're doing experiments to test the model itself. It's going to be more difficult to test a Titan scenario. That said, because it's largely controlled by thermal gradients, I have started to consider how I might can move forward. Once we get done with the modeling side, maybe there are some simple experiments we could do where we take a simple organic, we have some type of environment, we can set some type of thermal gradient and look at how it would freeze into there. But of course, we can't do on the same scale. But the model itself has been tested from terrestrial testing. It's been ground truthed. as a reliable model. As far as applying it to Titan, I have some ideas, but not any that have been done just yet.
Oh, maybe you said this, but I missed it if you did. Do you consider pressure effect also?
So, from what I understand with the model can what he found was that the pressure does not come into play until you are more than several hundred meters. Like we're talking probably a kilometer or more below the surface. So pressure isn't considered in this model because apparently the effect of pressure melting is negligible on the scales we're talking about.
All right, then I would suggest, because we have 3 speakers today, that we go to the next speaker. Let's thank Josh again. All right, awesome. So then our next speaker is going to be Carissa Campbell, correct? Is that the right order now?
I believe I am next, if anyone can hear me.
Yes.
It says I cannot share while another participant is sharing, so I'll just wait for that. Perfect.
Okay. Maybe I can use a minute to introduce you. So Marissa is currently a master's student, that's correct, with John Moore.
So I do believe Paul is there to introduce me if he is there, Paul.
Yeah, I'm here. So, so John is your supervisor. John is unfortunately not able to attend today, so he asked me to do Chris's introduction. So Carissa is actually a PhD student in John's lab. She formerly was a master's student in his lab, but I guess she loved it so much she stuck around for a PhD. Carissa mainly deals with, she works with the Mars Science Laboratory, the Curiosity rover, and she uses that to study clouds on Mars. I won't steal too much of her thunder, and I'll let her explain what she does with that.
All right, so can everyone see my screen and my presentation? Yes.
Mm-hmm.
All right, so thanks, Paul, for that introduction. I am a PhD student, and yes, I did love the program so much that I decided to stay. And my work is mainly with the Curiosity rover, trying to understand the altitude of the Martian water ice clouds that we do see at Gale Crater. So similar to Earth, Mars does also exhibit seasons. In particular, it has a dust and a cloud season. Since we are talking about water ice clouds, the aphelion cloud belt season is the most important one. It occurs during solar longitude 45 degrees and 150. That's kind of how we represent an orbit on Mars, is through degrees, as you can kind of see in that figure there. And in the red is when the aphelion cloud belt season would occur. So during this time, atmospheric temperatures are so low during aphelion, when Mars is further from the sun in its orbit, that it causes water ice to nucleate onto dust. As you can see on the right, the Hubble Space Telescope has seen this aphelion cloud belt during, it kind of forms during the equatorial part. And even on the surface and on the bottom, you can see that Opportunity also saw some really nice wispy clouds during the aphelion cloud belt season. In particular, for this work, the Mars Science Laboratory, which is still on Mars currently, landed in August 2012, most commonly known as Curiosity. I'll probably throw in MSL, Mars Science Laboratory, or even Curiosity as I talk through my presentation. And the most important instrument, as you can see, there's a variety of instruments on Curiosity. For this research necessarily is the navigation cameras, or the NavCam. They produce a 512 by 512 pixeled images, and they have a field of view of 45 by 45 degrees. And as you can see, they're kind of at the head of the rover, or the mast. Now, Martian water ice clouds have actually been viewed through atmospheric movies taken by these NavCams. So in particular, there's 2 different types of atmospheric movies. On the top, it shows the zenith movie, which has an elevation of 85 degrees, aka the zenith point. The point right above the rover is in every frame. Due to this having such a vertical pointing, we do have a time of sol constraint of plus or minus 2.5 hours from local noon, as we don't want the sun in our frames, as it will cause things to be very saturated, and I know the engineers would not be happy if I continued to point the sun directly into their camera. And then the second movie that we have is called the Super Horizon movie. It has an elevation of 38.5 degrees, so it's kind of pointed more above the crater rim. As you can see in the example here, you can actually see some of Mars there, which is quite cool in my opinion, but mostly it is kind of just above the crater rim. Now, because this one doesn't have such a vertical pointing, it does not have a time of sol constraint, so it can be taken at any time of a sol, mid-sol, late, whenever. Now, as I've been talking, these are movies, they are moving. However, you quite have to squint very well to see that there is clouds in these features. So what we have to do is we have to process them using the mean frame subtraction technique, which basically takes a sum of all the frames. There's 8 frames in every movie, and subtracts this sum from every frame to kind of pull out the changes that are happening in the frame, which would be clouds. And as you can see here, there's quite a change between the raw, which is on the left, and the mean frame subtraction movies on the right. So we've done lots of things with these clouds. For example, opacity has been calculated by Close et al. 2016. Diurnal and seasonal patterns have also been developed, including seeing quite interesting features such as gravity waves from Close et al. 2018. Ice crystal shape has also been determined from Cooper et al. 2019, and these people are all part of John's group here in the PBL. And for myself, I've actually estimated the altitude, which I do have a paper in review at the moment, which kind of takes these movies and tries to estimate the altitude of these clouds. So, in particular, the altitude has actually been measured on the surface of Mars before using the Phoenix Mars lander, and that uses the LiDAR instrument, which emits pulses of laser light to detect backscatter in the atmosphere. As you can see on the right, there is some measurements taken from Phoenix, where you can see where clouds and dust are. And in particular, Phoenix found clouds within the planetary boundary layer, which is the part of the atmosphere that's well mixed between the ground and the atmosphere. So we would expect clouds to be there because there would be lots of particles for the water ice to condense on. However, Curiosity does not have a LiDAR on board, so how exactly do we find this parameter without this instrument? Well, what we can do is we can actually estimate the altitudes with the observational results, aka zenith movies you can see here on Sol 1924, with modeled results from specifically the Mars Regional Atmospheric Modeling System, MRAMS, which was ran by Alexander Kling at the Ames Research Center for us. And what MRAMS does is it outputs a lot of different parameters such as temperature, wind speed, direction, for different points of altitude from 0 to 50 kilometers above Gale Crater. So for the observational results, what we can do is we can actually simply follow the clouds as they move across. Now, note that not all of the zenith movies in our hold can be analyzed because outside of the aphelion cloud belt season, there isn't a lot of clouds to work with, so there isn't a lot of features to follow. However, in the aphelion cloud belt season, we have a lot of great features, as you can see in the example there. So a lot more movies are considered usable or have really clear features to be able to follow this, since this was all followed by eye. And then features in this zenith movie, as you can see in the red circle there, are followed to determine an angular distance, where what we can do is we can take the field of view, which we know is 45 degrees, and the number of pixels in the frame, which is 512 pixels, to get an angular distance of degree per pixels in that frame. And as you can see in the trigonometry to your left, we unfortunately cannot find the altitude without the wind velocity, which unfortunately we can't get without the altitude. So we have to basically describe this in an angular distance, which is the change in angle over the course of the zenith movie, which follows the degree per pixel, as I mentioned, from the start to the end, as you can see in the red circle. Another parameter that we look for with this is also wind direction, which is simply just overlaying a compass rose, and we follow where the clouds move from. So the modeled results, as I said, that ranges from 0 to 50 kilometers above Gale Crater. Wind velocity is given in U, V, and W components. W is not necessarily used as it's quite negligible. And then what we can do, as you can see in the trigonometry in the bottom, is that you can take the angular distance and the altitude and the wind velocity, as I mentioned before, and translate that into angular distance so that we are able to compare the two parameters that we are able to find in the zenith movie to the parameters in the modeled results. And then what we can do is we can try to correlate that and say, well, where is it most likely that the observational results match with the modeled results at that particular altitude? So when we put this all together, we decided to put it as a likelihood more than a definitive value, since we're kind of comparing two things that aren't really exact values per se. And as you can see, there's actually two figures here. So if you take a look at the x-axis, that's your solar longitude, so that's your time of year essentially. We have our altitude on the y-axis, and we have a nice histogram which shows you how there's more definitive or really great clouds during the aphelion cloud belt season, which would be from, in this particular case, solar longitude 60 to 150. So when we take a look at all of this together, it looks a little bit of a mess, but when you look at just the aphelion cloud belt season, you can see that there's high likelihood of clouds in multiple bands in both the morning and in the afternoon. Now, one reason we split it between morning and afternoon is because there's actually two time periods of a sol when clouds appear, and we're not sure if they necessarily correspond to the same method of formation. Morning clouds might be due to really cool overnight atmospheric temperatures, which causes the water ice to nucleate necessarily without the dust particles, which would form clouds, while the afternoon would be water ice nucleating onto that dust particles being kicked up from mid-sol when atmospheric temperatures are warmer. So when we look at them from the two different graphs, you can see in the morning, there's lots of multiple bands that extend all the way from the crater rim from 2 to 3 kilometers, all the way up essentially to 40, 45 kilometers. However, in the afternoon, you can see almost a diurnal change, which has no altitudes above 35 kilometers, but the majority of altitudes would be below 30, with a quite big band between 15 and 30 kilometers. And it's also quite interesting that you can see a low likelihood of clouds between 20 and 40 kilometers between at the start of the aphelion cloud belt season and at the end of the aphelion cloud belt seasons, which might have something to do with the Hadley cells that transport water from the north to the south, changing as the orbit and everything changes in the atmosphere. So one thing we have to think about now, as I said, there's multiple bands of altitudes, is which likelihood altitude is actually the correct one. Well, last Mars year 34, we actually stumbled across a dust devil movie that was pointed at Aeolus Mons, or Mount Sharp, that actually showed shadows moving up the mountain, which is interesting because those shadows should theoretically only be coming from clouds. And it turned out that a zenith and super horizon movie were taken directly after this dust devil movie, which did show clouds. So what we can do is we can actually correlate the zenith movie angular velocity, as I kind of mentioned with my results before, with a direct velocity that we can measure directly from the mountain to be able to calculate an altitude from the surface of Gale Crater for the first time, which is fantastic because as of now, LiDAR would be the best suited instrument for this, but this is a great back of the envelope calculation. So I'm going to kind of go into how we do calculate the altitude from these two observations. So first we have to calculate the absolute velocity of the clouds, which is from the shadows moving across the mountain. As you can see in the figure here, what we try to do is we try to calculate the distance, which we can actually calculate from a digital terrain model, as we've been able to model the distances on the mountain, and we can use the X, Y, and Z coordinates and corresponding solar angle and the trigonometry shown there to be able to find this distance, where this distance is then divided by the duration between the first, which would be frame 11 in this case, and last, which would be frame 20 in this case, where the shadows are present. And then we kind of hold on to this absolute velocity. And with the zenith movies, is what we can do is we can use a similar method that I just showed you with the MRAMS model study, where we take the angular distance and do turn it into a velocity by dividing it by how many seconds were in the zenith movie, to be able to compare it with the cloud shadow movie, which was the dust devil movie with shadows, to be able to get the altitude as shown in the red box there. So when we kind of put these things all together, we can compare it to both the modeled results and just take a look in general of where these clouds are calculated. So last Mars year, we didn't get too many found shadows, unfortunately, because we stumbled upon it quite late into the cloudy season. But as you can see here, a lot of the results do match with the modeled and zenith movie results, which is great. That helps solidify more of the modeled results. There's actually an interesting thing where for Phoenix, they saw clouds within the planetary boundary layer, but on Gale Crater, where the planetary boundary layer is 2 to 3 kilometers because it's suppressed, we did not find any clouds within the planetary boundary layer, which is interesting because that's what we would expect. However, there's not that many to work with here, so this is kind of a small sample. But luckily enough, we are actually, the next uphealing cloud belt season in Mars year 35 is just starting as we speak. And we're actually starting to change some of the observations for this to be able to better find the altitude by, one, making higher quality movies, and B, making a larger frame size for the Cloud Shadow movie, which is a new name from the Dust Devil movie, which kind of incorporates a super horizon movie pointing and the mountain in the same frame. These movies here are of the new cloudy season that has just started, and as you can see, there are some shadows moving across the mountain and clouds to be seen. So this will be great to kind of pick up and start analyzing right away. Now, we have actually been very lucky on this season so far. We've actually seen noctilucent clouds on Mars, which are clouds that are still lit up from the sun even though it's set. So we were able to take a lot of twilight movies, which kind of occurred after 1800 but before 1900. When the sun is perfectly below the horizon. And as you can see, we were able to see really great cloud features. And in the top right corner is some of Mastcam images, which is the color imager on Curiosity that was actually able to see very nice wispy clouds as well. And that's kind of it for my research, and we're really looking forward to seeing what this cloudy season brings for us. So thank you, and I'll take any questions.
I had one question. If you could go back to one of your slides that has the distribution of clouds and altitudes. For the distribution, you say your likelihood is normalized, so why does that color bar not go from 0 to 1?
Oh, right. So it's an averaged likelihood. That's when you take the average and then you normalize it, it changes it so that all of the subseasons, so every 30 degrees solar longitude, is able to be compared with each other. Because for each subseason, they did have different high or low probabilities. We wanted to normalize it over the entire Mars year, if that makes sense.
Okay.
So I have a question. First of all, that was a really fun talk. I like the use of simple geometry like that to try and compare GCMs to unexpected observations. So I have some questions about that comparison. One of them is the wind direction that you get from your images should be fairly robust because it's not too dependent on the distance to those clouds. So I was wondering if you tried validating the GCM by just comparing only the direction of winds, like as a sanity check to make sure that the output of the GCM is reasonable.
So do you mean like with the new Cloud Shadow movie specifically?
No, just the other ones when you're just like staring up or at the horizon and seeing clouds move. Although the velocity of those clouds and their distance is degenerate, their direction of motion, I think, is fairly robust. So couldn't you just directly compare that observation to the results of the GCM to make sure that the GCM is on track?
I see what you mean. So even with the wind direction, it would still give us multiple altitudes that would correspond to the zenith movie values, especially either lower in altitude or higher in altitude. So even though we were able to directly see wind direction and see it in the model, it's hard for us to 100% compare since it still exhibits two different altitudes. if that makes sense.
Okay, so you mean that the wind direction in the GCM is a strong function of altitude?
Yes, it is actually.
Okay. So then my next question is, does the GCM, I mean, you seem to be leaning pretty heavily on the GCM for this in order to extract an altitude for the clouds. And I was wondering, if you're leaning so hard on the GCM, why not go like the whole way? Like, does the GCM predict where clouds should be? I mean, it's condensation, right? So presumably, even if the GCM doesn't do this intrinsically, you could post-process the temperature and pressure and like relative humidity of the GCM to make some sort of prediction or post-diction of where clouds ought to have been in the GCM?
No, that makes totally sense. And we did actually look at the relative humidity to try to see if there was an altitude that it did correspond to. However, when I was talking with the guy who runs these models, he was saying it was really still in beta mode regarding relative humidity and all the condensation type stuff. Because even though MRAMS was developed in 2001, being able to kind of constrain water, ice, and all that kind of stuff in any model is still quite tricky to do, that the people at MRAMS are still trying to figure that out at the moment. And this was kind of a way to prove, can we do this with the Zenith movies to get something out of the model? And then, of course, when we stumbled upon these shadows, that kind of really helps also solidify the model results. So that's kind of where this is going into more of the cloud shadow movie type stuff.
Okay, if there's no more questions, I think we should move on to the last speaker. And I believe, Nick, you're introducing the last speaker.
Yeah, that's right. So I'm introducing Kevin Moore, who's here in my group at McGill doing a PhD in Earth and Planetary Sciences. So Kevin did his bachelor's and master's in physics and astronomy at York, working on planets in binary systems, so simulations of that, and also brown dwarfs, I believe, in clusters, young clusters. And now at McGill is working on a much more geophysics-y geological project, which he will tell you about.
Okay. I'm back. Oh,
should I mute myself? Or?
Yeah, I would
mute myself.
Okay. Yeah. Okay. So, hey, I'm Kevin Moore. I'm a first-year PhD student working here at McGill with Nick. And for the past year, I've been working on modeling the water cycling and loss from the atmosphere of terrestrial exoplanets, specifically Earth-like planets that are orbiting M-dwarf stars, which are also known as M-Earths. So, Earth is the only place we know in the universe that has liquid surface water and life as we know it, and because of that, it is our template for a habitable planet. Now, this habitability obviously depends critically on surface water content, but it's not only important for biological processes, it also influences climate by regulating CO2 levels and the surface temperature through what is known as the silicate weathering thermostat. Now, in the silicate weathering thermostat, CO2 dissolved in rainwater weathers the land, and it releases chemicals that are transported to the oceans by rivers. In the oceans, marine animals precipitate calcium carbonate shells, and when they die, their bodies sink to the bottom of the ocean. They become sediment, and it's recycled back into the interior of the Earth, where the carbonates and silicates recombine, and carbon dioxide is released back into the atmosphere by volcanism. Now, this is also a very important stabilizing feedback for Earth, because if there was a higher surface temperature and there was more CO2 in the atmosphere, that would increase the weathering rate on land. But because more CO2 is not being expelled from volcanoes, the increased weathering rate would act to lower the CO2 levels in the atmosphere and bring us back to that comfortable climate we have now. So a critical aspect of this model is requiring both exposed land and oceans to be present on the surface of the planet. So planets that are dry and have no surface water, or planets that are ocean covered and have no exposed land, really won't benefit from something like this to really stabilize their climate. So there's obviously water on the surface, we know about the oceans, but there's also water sequestered within the Earth, and that leads us to Earth's deep water cycle. So this is a very simple two-box model of Earth's water cycle with two reservoirs, the surface reservoir and the mantle. And in this model, water is degassed from the mantle through mid-ocean ridge volcanism, and it is regassed from the surface back into the mantle by subduction of hydrated oceanic crust. So the high temperature pressures within the mantle, the viscosity is very, very high, and you have a very, very viscous solid flow of the mantle. This solid flow of the mantle, which is about 10 to, so the mantle is about 10 to 21 times more viscous than water. So it's a very slow flow, but it is still a flowing mantle. And the flowing mantle coupled with the brittle lithosphere is what gives us the theory of plate tectonics on Earth. So Earth is the only planet we know that has plate tectonics for sure. That leads us back to it being a great template for being a habitable planet. So the biggest uncertainty in modeling this is how much water is actually in the mantle. So it's expected from studies now that there's anywhere between 1 to 2 oceans sequestered within the mantle, but there could be, based on the mineralogy of the mantle, it could hold up to about 12 oceans worth of water. So if we can pin that down, we can get a little more accurate. But we can model this 2-box regassing and degassing by making the rates dependent on seafloor pressure. So to first order, depending on seafloor pressure means that it depends on the amount of surface water on the surface. So if you had more surface water on the surface, the degassing, which is from mantle to surface, would be suppressed, and the regassing would increase because you have more water. You're able to stuff more water down into the mantle. So if we look at this model, we start with the same amount of water on the surface and in the mantle, and we run it for 15 billion years. We can see that for the most part, water cycles from the surface down into the mantle. And if we look at the rates, we can see that the regassing rate, which is surface to mantle, is much higher than the degassing rate up until later in the evolution. And later in the evolution, we see that the mantle water and the surface water contents seem to settle out. And since the degassing equals the regassing at the end of these simulations, we've reached a steady state. So Earth for the past 2.5 billion years has been in a relative steady state with the levels of the oceans with respect to the continents. And so this is really interesting to reproduce with such a simple 2-box model. So most habitability studies focus on sun-like stars because that's what we're the most familiar with because of our own solar system. But about 70% of stars in the galaxy are actually M dwarfs, and about 40% of those have at least one rocky planet within the habitable zone. Unfortunately, these M dwarfs are very active during their very long evolution onto the main sequence, and so these planets are in a much stronger radiation environment than they would be if they were around a sun-like star, for example. So just as a reminder, the habitable zone is the region around a star where a planet is receiving the amount of flux to have surface liquid water on its surface. So you can see by this comparison with the solar system and the TRAPPIST-1 system, these planets orbit much, much closer than even the orbit of Mercury around the host star. And that's because the stars are much, much smaller and they're much less luminous than the sun. But because they're orbiting so much closer, they're receiving a lot more radiation. And so we have to worry about this very active radiation environment, especially because it exists for so long around these M-dwarf stars. So the main thing that I'm worried about right now is losing water from the atmosphere through the photodissociation of H2O. So on this plot, you can see the XUV radiation, which is the extreme ultraviolet radiation of three M-dwarf stars, which is orders of magnitude higher than we're receiving at Earth. But it does decrease with time. Even though it decreases with time, though, there's obviously a significant amount of time where this XUV flux is bombarding the atmospheres of the planets. So if the planet is in a runaway greenhouse regime, that means its surface temperature is so high that all water evaporates and exists as steam in the atmosphere. And if it is transported high enough in the atmosphere, it can be photodissociated by this XUV radiation, so the H2O molecules are ripped apart, and the lighter hydrogen is then lost to space, while the oxygen either builds up in the atmosphere or reacts with the surface. So on Earth, we don't really have to worry about water reaching high in the atmosphere because of the cold trap. So at the top of the troposphere, we have a temperature inversion, and any water that reaches that level condenses and comes back down. So we have a relatively dry stratosphere and don't have to worry about water loss on our planets. But around these M dwarfs, planets form around 10 to 100 million years. And specifically those two M dwarfs in the blue and green, you can see that their planets spend a very long time after they have formed, potentially in this runaway greenhouse regime. So they could potentially be losing water for a very, very long amount of time. And if they don't have a lot of water, they could lose it all. But yeah, so including this loss and a bunch more reservoirs and a bunch more fluxes, you can see that this cycling and loss is much more complicated than the very simple two-box model I showed at the beginning. But for now, I'm just focusing on the degassing and regassing, the two-box model, but now I'm adding loss to space into the model. So now I've added loss into the model. I parameterized it as a decreasing exponential based on the plot I showed a couple slides ago. The loss rate is 10 times the initial degassing rate, so we can see loss occurring, and the loss time scale is about 100 million years. So you can see that surface water is being lost to space, and about 25% of the initial surface water is lost to space. So that seems like a pretty significant amount. But you can see that after around 1 billion years, when the mDOR's activity has died down and there's a lot less XUV flux hitting this planet, the mantle actually cycles some water back up onto the surface. So while we did lose a lot of water, some that was stuffed inside the mantle comes back up and helps bring up the ocean levels a little bit higher than they were. So again, this seems to look like it settles out, like when before I added loss. And yeah, the degassing and regassing equal one another at the end of this. So even with this little bit of amount of loss early in the evolution of this planet, we can still reach a steady state in mantle and surface water. So that's interesting, but what if we have even more extreme loss? So if I make the loss rate 10 times more than I did in the previous model, we can see that we lose a lot more water. So on the previous model, you can see we get down to about 1.4 times 10 to the 21 kilograms of water, which is about 1 Earth ocean. And on this one, we have a period of time where there's no water on the surface of the planet. Since there's no surface water, there can be no regassing. So the interesting part about this is that you can see the mantle water begins to decrease as it is degassing back up to the surface. But there still seems to be no water on the surface for an amount of time. So that means the degassing, the water that is degassed is immediately lost for a time until the activity dies down. And then we can see the surface water begins to recover. So an ocean is recovered basically from water that was stuffed into the mantle. So that's cool to see. It kind of looks like it's reaching a steady state, but the simulations don't really run long enough, so it's hard to say if it's reaching a true steady state. So the real concern of these models is how much surface water is on the planet at the end of the evolution, because that's really the thing we want to be looking at. So we can place that in, we can place a planet based on its surface water into one of the 3 regions I have denoted here. So a dune planet at the bottom there has less than about 1% of an Earth ocean on its surface. But because there is exposed land and there is water on the surface, the silicate weathering thermostat could potentially be buffering the climate there. Up on the top, you can see we have water worlds, so greater than about 10 Earth oceans. You have a water world, there's no exposed land, so you really wouldn't benefit from that silicate weathering thermostat. You could have some seafloor weathering to try to buffer the climate and CO2 levels a little bit, but it would not be as efficient. And then in the middle there, you can see a habitable planet. So that's roughly an Earth-like planet. It's got some water on the surface. It's got some land exposed. And so that's just the region in the middle there. 2 more regions that I have labeled on here are if you have too much surface water on a planet, so greater than about 100 oceans worth, you develop high pressure ices at the bottom of the ocean. And that would obviously suppress the regassing and degassing rates. And then we couldn't really use our simple 2-box modeling. But for now, we don't get to that amount of water, so we don't have to worry about it too much. And then the limit on the right is, obviously, I mentioned the mantle can hold up to about 12 oceans worth of water, and any more than that, you can't stuff any more water in, so it would just remain on the surface. So we can run a slew of simulations with various initial conditions, different surface and mantle water inventories, and different loss rates and loss timescales, and we end up with this. So a lot of planets. Oh, I should mention, I test 3 models now. So at the beginning, I was only testing the seafloor pressure dependent model, but now I'm also testing a mantle temperature dependent model. So the degassing and regassing rates are dependent on the mantle temperature, and a hybrid of the 2, where the degassing depends on the seafloor pressure and the regassing depends on the mantle temperature. So starting with a bunch of different initial conditions, a lot of planets become water worlds. Some planets are habitable, some planets are dune planets. But an interesting thing to note here is that planets can move across these regimes as they evolve. So some of these water worlds become habitable planets as they evolve. Some of these habitable planets lose a lot of water and they become dune planets as they evolve. And losing water as you evolve, you obviously have to be concerned with if there's not enough water on the surface at the beginning and you have a substantial loss rate, you could potentially be losing all of the water on the surface and end up with a barren planet. And actually, while that's a concern, only about 12 of these 243 simulations actually end up with any water on, or without any water on the surface. So for the most part, starting with various amounts of water and with different loss rates and loss timescales, these planets usually end up with at least some water on the surface. So I'll just leave it with my conclusions that even with loss, these emeralds can retain water on their surface throughout their evolution. If a planet loses all of its surface water by loss, then if there's water inside, sequestered in the mantle, then it can be used to rejuvenate a desiccated surface. But the question remains, are planets with both land and ocean common? Maybe water worlds are more common, maybe dune planets are more common. So I think a more extensive parameter space search will help us address that question a little more. Thank you, and I'll take questions.
Can you unmute yourself?
I think I am unmuted.
Cool, and is your volume up so you can hear people asking questions?
Yeah, I think my volume's up.
Maybe I'm supposed to act as MC.
So
Go ahead. Oh, my mic's still on.
Yeah.
all right, I guess I'm MC. So are there any questions for Kevin?
Brett Gladman here. Can you hear me?
Yep.
Hi, Kevin.
Okay, we're good.
My question is about what are the uncertainties on both the subduction rate and the degassing rate, depending on the temperature of the planet?
Uncertainties on the rates.
So, I mean, you have a parameterization about how the degassing depends on, if you've got that early slide.
This one or this one?
Yeah, I think the one after this is where you show you just got it proportional to the seafloor.
Yep.
So these, is there any, in other words, how much uncertainty given the fact that these are super Earths and their geophysical conditions are different? Obviously, if you're pumping the water out of the mantle faster, it will change your... You believe that these are the only parameters that are affecting the outgassing rate?
No, it's just a very simple parameterization to allow the differences between different parameterizations, so the seafloor pressure dependent, the mantle temperature dependent, and then the hybrid of the two, just to see how they can affect the evolution and the way the water is cycling. But obviously it could be a lot more complicated. But for now, we're just focusing on an Earth-like planet that has these.
Right. So if you ever get into a phase where the water goes away, do you think that could shut off plate tectonics and then completely shut down the re-outgassing?
Yeah, we've talked about that, and we haven't really gone forward with addressing it because it's such an uncertain question. But it is something that I'd like to look into a little more as I move forward.
Yeah, given Venus is the analogy, right?
Yeah.
Thank you.
All right, are there any more questions? Are there any more questions? If not, I will hand it back to Bjorn. We're on time. Okay, well, Bjorn, if you were talking, we couldn't hear you. So I guess we will see everyone for the next TEPS seminar, whenever that is, in a couple weeks.